Hi, in the previous video we have implemented the node class. In this video we are going to implement the binary search tree class. So class binary search tree, it's going to have an object as usual. It's going to have an init, so def init with the self, and we just have to define a root node. It's going to be a none at the beginning. So let's implement the insert method. We have a self and we have a data we would like to insert. If not root, it means that this is the first item we would like to insert because the root node is going to be a null. So if not self root, it means that this is the first item, so we have to instantiate a node for the root with the data. This is why we define the constructor for the node like this. It's very important, I'm not sure whether it's clear or not, that we are able to reach the items in the tree only with the help of the root node. So that's why we just have to store a reference to the root node, and every single operation is going to look for that given node, for example where to insert the given node or how to delete a given node. We start at the root node and we have to find a given item. Okay, and else we just have to call the self.insert node method with the data and the self.root. Okay, so let's implement this insert node method. We have the self, we have the data we would like to insert, and we have a node. Okay. We just have to check that if the data is smaller than the node.data, what does it mean? That the given item is smaller than, for example, the root node. So if we insert the first item, it's going to be the root node by default. But anyways, if we would like to insert 4, we have to start at the root node and we have to compare them. The 4 is smaller than 12, so we go to the left. We come to the conclusion that there's a null, that there is no children at all, so we insert it to be the left child of the root node. What about 5? We come to the conclusion that 5 is smaller than 12, so we go to the left. Okay, 5 is greater than 4, so we insert it to be the right child of 4. So this is why we have to decide that if the data is smaller, and we have to check that if that given node, so if the left child is not a null, then we have to call this insert node recursively with the data and node.leftChild. Okay, else, what does it mean else? We check whether that node left child, so we check whether is there an existing left child. If there is, then we are able to call it recursively. Else, we just have to insert it. So node.leftChild is equal to a new node with the data. For example, this situation, we insert 5, we start at the root node, we go to the left because this is not a none. So there's an existing node. Okay, so we call recursively this insert method on this node. We come to the conclusion that we have to go to the right, but there is no right child for this node 4, so that's why we have to instantiate a new one. So we instantiate a new one. And else we know that the data is greater than the node.data, so we have to consider the right subtree. So if the node.rightChild, which means that if there is already a node inserted, so the right child is not a none, we just have to call this insert node method recursively with the data and the node rightChild. And else, we know that there's a none, so basically there is no right child, so we have to instantiate one. Of course, the right child is equal to a node with the data. Okay, so that's all about insertion. I think it's quite intuitive for binary search trees that we have to check that, okay, we would like to insert the data. If the data is smaller, we have to consider the left subtree. That's why we consider the left child. But again, we have to decide whether is there an existing node, because if there is, then we have to call this method recursively on that given node, and else we know that there is no child on that given position, so we just have to instantiate a node. And we have to do the same for the right child, because if we know that the data is not smaller, it's going to be greater, you may pose the question that, okay, maybe we should handle the situation when the data is equal to the node.data. So we would like to insert some data that we have already been inserted. Of course, I'm not going to handle this situation. Maybe we could do some update. Anyways, it's not that important. Okay, so that's all about the insert operation for a binary search tree. It's very important that it has the running time complexity logarithmic n. I think that we use something like this. Okay, ordo log n. Why? Because on every iteration, as you can see, we have the recursive method calls, but we discard half of the tree basically, because we just have to decide that whether we go to the left or go to the right. Okay, so that's why the insert method is going to have logarithmic time complexity. It's very important that if the tree is balanced, if the tree is not balanced, then it can reduce to ordo n. So basically that's why AVL trees and red-black trees are needed. We are going to talk about balanced trees. It's very important that if this tree is balanced in the sense that the left subtree contains approximately as many items, as many nodes as the right subtree, it's approximately balanced, then the running time is going to be logarithmic for the operations, but it can reduce to ordo n. How? For example, we keep inserting items from a sorted list, 1, 2, 3, 4. As you may guess, it's going to end up with a linked list. We are going to talk about this problem in the coming sections, so don't worry, we are going to focus on binary search trees at the moment. Thanks for watching.